things. So if we can kill these front lights, that would be wonderful. It's great to be on the North Shore. Just by a show of hands, who is currently wearing thongs? Yeah, nice. That's what I wanted. Good. Growing up on the North Coast, so I feel like that's very much something we have in common. I would rather be in thongs right now. So, Science versus God is a very dramatic kind of title. I want to get at it in a sort of roundabout way. Something specifically about science, which I think can tell us quite a deep lesson about how to think about this whole area, and then we'll try and sort of drive the point home at the end. So let me start with an interesting puzzle that comes up within my field of astrophysics. One of the great things about being an astrophysicist or being an astronomer is that no one really has to talk you into doing it. The reason for that's quite simple. It's because the universe looks a bit like this. You only have to stand outside on a lovely starry night, and the darker the night, the better, to appreciate the amazing beauty of the night sky. And if any sort of curiosity clicks off in your head, then no one really has to talk you into being an astronomer after that. One of the things we see in the night sky, one of the things that's so wonderful about it is, just like any sort of great artwork, is the harder you look at it, the closer you study it, the better it looks, the more beauty we see. When you build a new telescope, you don't always know what new thing's going to turn up there, but you're almost certainly going to see something ridiculously beautiful. That is the Horsehead Nebula. This is where stars are born as gas clouds collapse. We can see stars going through various stages in their lives, for example. We can see where when a star runs out of a certain type of fuel, our sun is burning hydrogen, for example, when it runs out of that and has to fire up something else, it's going to go through a bit of an episode of heating up and contracting and expanding. It'll throw off a bit of the outside gas as it does that. And what we will see from Earth is known as a planetary nebula. And they look like this. It looks pretty good on the screen. Looks not too bad at the back on that screen there either. You really do owe yourself a nice quiet evening in a nice dark room with a really high-resolution screen and the Hubble Space Telescope website and a nice red and some Beethoven, and really make a night of it, okay? We can also see when stars get to the end of their lives and run out of fuel completely that they sometimes blow up and leave remnants. This is a supernova remnant. It's where a star completely exploded and drove a whole heap of its matter into surrounding space. And of course, there's the family photos where all the stars get together in a galaxy. This is what we see in the universe around us. Now, if you are like me, a complete nerd, then there's another type of beauty out there. Right? Not only are there these beautiful patterns on the night sky, which all of us can see directly, but if you look deeply enough into the way the universe works, we see mathematical patterns there. If you can speak that language, then there are very beautiful patterns there behind the scenes, what we call the laws of nature. In particular, we can understand the largest things in the universe in terms of these basic bits of the universe, the smallest pieces, how they act together to form the things around us. I want to give you a very brief overview of how that works, because it'll be important to set up what comes next. Let me start from the bottom up. Here are some of the biggest things in the universe. Let me introduce the smallest. What particle physicists do is get what's called a particle accelerator, and you get two bits of matter, usually two protons. You fire them at each other as hard as you can and see what comes out of the wreckage. Basically, you're trying to rip things apart into the smallest pieces. All right? When we've done that with the matter that we're all made of, the smallest pieces turn out to be just three things. All right? This might win you a pub trivia quiz, so pay attention. Okay? They are known as the up quark, the down quark, and the electron. Three pieces, right? When you get down to the Lego set of our universe, there's three types of basic brick. Okay? What we can do with those is build bigger things out of them. So the first thing we can do is build what are called protons and neutrons. If you're playing along at home, two ups and a down makes a proton, and an up and two downs make a neutron. The names up and down don't mean very much. These things are so small and so simple, there's not really much else you could name them, so you just pick something short. What can we do with protons and neutrons? Let's keep building things up. We can make atoms. So the proton and the neutron there, we combine them in the centre to form a nucleus. The electrons will orbit nicely around the outside, and we have there an atom. Which atom this is depends on how many of these protons you've put in the centre, and the great thing is there's different ways of doing that. So there's a whole host of things you can make with this Lego set just corresponding to how many protons you've stuck in the middle. All of those different things are called the elements. My apologies if I'm giving anyone some chemistry flashbacks from high school here. It'll be gone shortly, don't worry about that. One of the great things about these elements is when we put them close to each other, because those electrons going around the outside keep orbits, when we put nuclei close to each other, it can be the case that electrons, instead of just sticking to their own nucleus, go on a complicated orbit around the whole thing, binding it together. And so we can bind nuclei together, and that, in 2 sentences, is chemistry. Okay? That's as much as you probably need to know for everyday life, to be honest. Our universe is really good at doing this. So, for example, that is DNA. Okay? You take 5 different types of elements, hydrogen, oxygen, nitrogen, carbon, and phosphorus. You put them in this arrangement. You let the electrons do their thing of binding the whole lot together, and you can literally write the instructions for making a person. Okay? There is some combination of these letters that specifies you. It's in all of your cells right now, and for enough money you can get it sequenced for no reason. It'd be cool, but I don't know why. Our universe is really, really good at this, because what these actually encode are certain ways of clipping proteins together. And if you do that enough, in the right order, you can make a biological cell, which is a monumental piece of machinery. Each cell, for example, has its own postal system. If you want to get some particular chemical from one side to the other, it'll have an address put on it. It'll be packed into a truck. It'll be sent down a little highway. The address will be checked. If it's the correct address, it'll be unloaded and put to use where it needs to go. So molecules can do all of that at that level. And of course, if you put enough cells together, you can make munchkins. So here are some that I prepared earlier. So in short, with some assembly required, you can turn the basic bits of our universe into the things we see around us, right? Now, it's a little bit more difficult than I've said there. Better methods are available. But that's the short story for... Some of you are on board. That's the short story for how you build up complicated things. So if that was all too much science at once, let me summarise where we've arrived so far. You're made of stuff. As a scientist, we look at that stuff and we want to know why it is what it is, right? Having broken down into the smallest pieces, we then want to know why they have the properties that they do. And what we find at the very bottom is a set of properties of the stuff in the universe. Things like, how heavy is an electron? There is no theory that tells us what that number is. We can go out and measure it to astonishing accuracy, but we sort of have, that's kind of cheating. We had to ask the universe. We didn't get there ahead of it. There are actually quite a few of these numbers. How strongly do different charged particles interact with each other? How strong is gravity? When we break it down to that level, we've reached a very deep set of questions about the universe. This is something that theoretical physicists do. You want to know why the universe is the way it is, and one way to attack that question is to ask, what if? What if the laws were different? What if this set of laws or that set of laws were the way that the universe worked? What if we had a different Lego set, or we changed the properties of that Lego set? Right? What if gravity was stronger? What if the electron were more massive? Is that slightly cut off? Never mind. What if atoms were more or less stable? A particularly weird one is, what if there were different numbers of dimensions of space and time? Right? It's all mathematical. We can do this with equations. It's great fun. Or horrifying, depending on how you feel about mathematics. So we can ask the question of what kind of universe could there have been? How could our universe have been different? We ask this question to try and get at the deepest properties of our universe to see what's going on. Here's the interesting thing. Science has been doing this for about the last 40 years, and it turns out that when you start to mess around with the basic properties of the universe, you a lot of the time end up totally ruining the universe. Let me explain what I mean by that. Let's return to our atom with the electron going around the outside. You remember that those protons and neutrons sticking together in the middle are what created the whole periodic table, which gives us all those different chemical elements with all their different reactions, which produce life and everything as we know it. With a remarkably small change to the basic properties of our universe, we can arrange it so that those don't stick to each other. The basic stuff of our universe now fails to stick. Here's why it works. In the universe, energy is kind of the currency. Right? If you want something to happen, you better be able to pay for it with energy. Because if you haven't got enough energy, it's not going to happen. Einstein taught us that E equals mc squared, right? There is one equation in this talk, and that was it. I hope we all handled that nicely. Mass is a form of energy. So when you start messing with the masses of these fundamental particles, how heavy they are, you don't just make everything a bit heavier or a bit lighter. You start to change what processes in the universe it can afford and which it can't afford. Here's why that's important. If you want something in the universe to be stable, to just stay there, like, for example, you would like your DNA to pretty much just stay there. We don't want that changing at random. A way to make something stable in this analogy is to make it broke. Make it so it can't afford anything. Have it in a low energy state where nothing else can happen. If you start messing around with the masses of the basic stuff of the universe, suddenly things that were stable, like nuclei, are now unstable because it has enough energy to kick that neutron out of there, or kick a proton out of there, or kick anything else out of there, and now nuclei aren't stable. Actually, we can make this even worse. With another slight change, we can have it so that electrons, instead of orbiting around the outside, spiral into the centre, and you don't even have nuclei anymore, you just have clouds of neutrons. This is bad news. Here's why. Here's the periodic table. Just as an aside, in case you're interested, this is the astronomer's version of the periodic table. It tells you where all these elements came from, where they are produced in the universe. So the ones that are left over from the Big Bang are in purple. Small stars get hot enough to make a little cluster up here of quite important elements. You need a larger, hotter, bigger, badder star to make the green ones. And even those aren't big enough and hot enough to make all of them, so what you need to make the rest of them, these sort of pinkish ones, are supernovae. You actually need those stars to blow up, and in the explosion itself, these ones get made. Including that one, which is gold, by the way. So if you're wearing a gold ring, that's where that came from. Okay? Bit of an aside. Right. If we mess around with the universe too much, so that now nuclei are unstable, the periodic table now looks like this. Nothing sticks to anything else. That story of, let's take the smallest things in our universe, you start with quarks, we make protons, we make nuclei, we make atoms, we make chemicals, we make biological chemicals, we make cells, we make munchkins. That whole story now gets cut off a bit too early. We have quarks, we make protons and neutrons. That's it. For example, this might appeal to some people. In this universe, a chemistry exam would go like this. Question 1, what is the element? Hydrogen. Question 2, what is the chemical reaction? Because there's only one. You put 2 hydrogen together and you can make a hydrogen molecule. End of exam. That's it, we're done. Actually, you can do other little tweaks where instead of hydrogen being the only element, helium is the only element. Okay? Some of you are there ahead of me. That chemistry exam goes like this. What is the chemical element? Helium. End of exam. There are no chemical reactions. That's it. Okay? This fact about the laws of nature as we know it, that very small changes to these numbers we don't know why they are what they are, but if you change them a little bit, you end up ruining the universe for any kind of complexity, really, including life, is known as the fine-tuning of the universe for life. I gave a talk like this last week. And there are a couple of youngsters in the audience who looked up at that picture and had no idea what it meant. Okay, so hopefully you're all old enough to know what that is. It's a radio dial. Okay. But that's the idea, right? You want to do something interesting, you've got to nail those properties right on. If you go a little bit one way or the other, you just get boring static. If you want that particular classic FM or whatever it is you're after, you better nail it right on, because a false step one way or the other, you could end up with static or, Today FM or something, some other disaster, right? Okay? There are other ways to ruin the universe. So one of the things I do in my research is we take a computer, and within the computer we represent parts of the universe with what's called a particle that sort of represents a bit of the universe. We have a whole heap of those who represent a lot of the universe, and then we sort of teach them the physics that we know of the world around us. They will attract each other via gravity. If they get close, they will feel each other's gas pressure, just normal sort of air pressure, type pressure. If they're hot, they'll glow. If they're very dense, they'll form stars. Those stars, if they're big, will blow up at the end of their lives. We can put all of those within an expanding universe on a computer. We code all of that up. We have about 5,000 computers connected together, and we run this thing for about a month and a half, and we hope that nothing happens to the computer in that month and a half. And then we make a pretty picture at the end of it, which looks a bit like this. So, it's a pretty movie. Our universe as we know it starts off smooth, but not perfectly smooth. And so the moral of this story basically is the rich get richer. If there's a blob of matter in the universe, because of the pull of gravity, it'll attract other things to it and become even more massive. That's the short story of how all of this structure forms. On top of that, we have other forces pushing things around, and in particular, you might be able to see stars are being made and blowing up at the very densest parts of this structure. But overall, the universe forms what's called the cosmic web. As the densest part of the universe starts to empty out the bits in between, those are called voids. The parts that they're sort of wrestling over form a filament-like structure, and then at the sort of intersection of these filaments are what are called knots, where galaxies form and clusters of galaxies. So we do all of that in a computer, and then we try to find out whether at the end of the day we've made something that actually looks like the galaxies we see around us in the universe. And it's never quite perfect, so we tweak things a bit and try again. Or we throw a bigger computer at the problem and see what happens. That's the how to build up interesting things and interesting structure, the big story of that in our universe, just as I told sort of the small story on the way up before. There are ways to ruin this story as well. For example, if gravity itself were too weak, then things would sort of bounce off each other instead of being drawn together. The main effect there was anything that's sort of big and heavy gets even bigger and heavier still, and so we can make stars and planets and all that sort of thing. You make gravity too weak, and that doesn't work. There's another thing in our universe called dark energy, which I won't go into in too much detail, but there's a very easy way to totally ruin the universe using that as well. If it's too strong, the universe expands too fast, and gravity never gets a time to sort of grab things around it before the universe expands away. So what happens in that universe is rather than all of the interesting stuff we see around us, there would be lonely protons sort of in the middle of an awful lot of empty space. Maybe every trillion years or so, another particle would come past, bounce off, and head out into the universe. Right? There's a very boring children's story called The Lonely Proton in the working here. Not much happens. That's a very easy way to totally ruin a universe. Nothing interesting will happen because nothing ever gets together to make something interesting. All the universe sort of expands out into a one-piece Lego set. There's also problems if you make gravity too strong, by the way. Stars in our universe are basically a balance between two forces. Gravity, of course, is pulling in, as it always does. And so if a star is going to be stable, something better be pushing out. And that thing is heat. The ordinary pressure of hot things, hot gas, is pushing out. But because that heat energy will leak away from the surface in what we call sunlight, we need nuclear reactions at the centre to keep the centre hot. And voila, you've made yourself a star, if you want to try that at home later on. There's a balance there. if your star contracts a little bit too much, it'll heat up, get a bit more pressure, and sort of fight back to where it was and basically stay where it is. So the sun, from day to day, from year to year, millennia to millennia, doesn't really change that much because these forces are in balance, and anything that throws off that balance quickly dies away as we get back to the standard state of the sun. However, if we make gravity too strong, instead of that nice balance, what we get is an overreacting balance. What will happen is, instead of the star getting back to where it was, any perturbation, any sort of oscillation in the star will grow instead of dying down, and the whole thing eventually will blow up. That is another way to completely ruin a very important source of energy in the universe, stars. So, let me introduce the book that I've written. It's available up the back. I hope that gentleman is enjoying it. Is it good? It's excellent. Very good. There's a good review. If you could pop that on Amazon, that would be much appreciated. Please carry on. I didn't mean to sort of... the first 6 chapters of this book basically outline all the different ways you can ruin a universe. Okay? If anyone has aspirations of being a supervillain of any kind, there are some great ideas there for a doomsday device. If you can just manage to change the laws of nature, you can totally ruin everything. I wrote it with my, boss, colleague, Geraint Lewis. The first 7 chapters we wrote together, and then the last chapter we wrote separately. Geraint is an atheist. Okay? We wrote the first 7 chapters together, because basically the science I've been explaining is pretty much all there in the scientific literature. There's not that much of a debate about it. A Christian and an atheist can sit down, write a book together, and almost agree on everything. There is, if you want to buy the book later and check through it very carefully, one footnote which begins with the sentence, "At this point, our heroic authors got into a disagreement about ... Okay? But the rest of it we wrote together. Okay? What we didn't agree on is chapter 8. What does all of this mean, right? You change the laws of nature, ruin a universe. Okay? What does that mean? What should we conclude from this? What Geraint wants to say, his point of view on this, is that there is something called the multiverse, which, if you can see it there, has turned up in comic books. This is Infinite Crisis, Fight for the Multiverse. Okay? In the academic literature, we talk about the multiverse quite a bit. Unfortunately, there's not a lot of Batman in that literature, so you'll have to enjoy him on the screen for the moment. I'm not sure what that punch is accomplishing, but he's there anyway. Here's the idea. When something unlikely happens, maybe it just means that there were a lot of different attempts at doing that unlikely thing. Why does someone win the lottery when it's so unlikely? Well, because lots of people buy different tickets. So it seems like our universe's ability to make and sustain life is an unlikely thing, something that's quite rare. So how did this universe happen at all? Maybe there are other universes out there. Right? That's the tickets in this lottery, but they've got to be universes, right? They've got to be places where the laws of nature are different. So the idea then would be that the universe as a whole takes on perhaps this sort of structure. There is different sort of pockets, different bubbles of universe where there are different laws. Most of them, for the reasons that I've said, if you just pick some set of numbers, set of properties at random, are dead, but every now and then one of them is just going to get it right. And that's, of course, only in those universes does anyone stand around and scratch their head as to why they're in a universe which supports life. That's Geraint's perspective on this. So the picture we get from this idea, from the multiverse, is that our universe is almost alone amongst all the other multiverses as in doing something interesting. Amongst this multiverse, there's an awful lot of other dead universes, and ours, by chance, got the recipe right and made something interesting. So that's kind of the picture that comes out. Now, that could be true. And I'm a scientist, so I want to know whether that idea is true, and we're testing it, and there's things to be said pro and con. But I think even if it was true, there'd still be some deeper questions there about why the multiverse was there at all, and why it was a multiverse which allowed enough variation to hit upon the right recipe in the first place. What I defend in the book is the idea that there is a fine tuner. Here's the way I like to think about this. Suppose there were some chess pieces on a chessboard trying to work out how their universe worked. They would be doing science. They watch the way the things around them react and move, including themselves, and try to generalize into the laws of their environment. Okay? They would notice that bishops always move diagonally. That would become a law of nature from them. They would classify the different types of things there are in their little universe. And one day, one very clever chess piece might actually write down the rules of chess. They would be, that little sort of chess piece Einstein would be, sitting there looking at the rules of chess. In terms of analysing why things move as they do, their job would basically be done. It'd be over. Would all of their questions have been answered? I want to say no, because there are still a whole heap of questions that they could have about their universe, but which would not be explained by the laws of their universe. Why aren't we playing checkers? Would be one question. They might even notice that if you change their rules a little bit, you get a much less interesting game. And so perhaps they would speculate, in their case correctly, that actually their rules were made up for some sort of purpose. Amongst all the possible sets of laws, theirs were chosen because they achieved something. One of the advantages that this explanation has, which is an advantage of any explanation, I want to say, is that it takes a whole massive set of possibilities and allows us to focus in on some that are more likely than others. Okay? All the possible rules for how things could move around, if you say, but now we have an interesting game with interesting strategy, now there's a smaller set which become more likely. This property of good explanations is a bit like the game Guess Who, if you're familiar with this game. Two players look at all these people, they pick one of them on a card, and then you have to ask questions from your opponent to try and work out who they have before they guess who you have. The really good questions, good questions and answer sets together, I have to say, are the ones that flip down a whole heap of possibilities. Okay? For example, if you ask, does your person have a moustache and a beard, then that's a great question if they say yes, because it's Richard. He's the only one, for some reason, that has both a moustache and a beard. All right? You can obviously imagine the game I had as a child, which went catastrophically for me. You can just fill in the rest of that story yourself. Okay? Where there are a huge set of possibilities, an idea, a hypothesis that helps us narrow them down by a lot is a good explanation. So suppose at some point in the future, at some conference, Albert Einstein's great-great-great-great-great-great-great-great-granddaughter, Alberta, walks up to the board, and I don't know why Alberta's funny, but everyone laughs at it. Okay? I was recently in the US. Everyone in the US laughs at it as well. Maybe it's a Canada thing for them. Alberta walks up to the blackboard and writes down a set of equations, and physics is over, right? Like the chess pieces working out what the rules of their game is, we've solved our universe. Right? I like to think, along with the comedian, that at this point all of our reality will dissolve and a sign will come up saying, level 2. Not my joke, but very good. What do we do then? Have we answered? I mean, one of the reactions might be, let's just high-five and go to the pub, we're totally done here, right? But we still might have a whole heap of questions, okay? For example, why those laws and not other ones? Just like the why aren't we playing checkers question. And fine-tuning says, actually, probably, this is one of a very small set of laws which will allow something interesting to happen in the universe at all. Most of the other laws won't do anything interesting. If we took this chalkboard, this particular chalkboard would have the actual rules of our universe, but we could imagine a whole heap of other chalkboards with other possible rules, right? We have all of maths available to us. We have every equation there's ever been could describe our universe. Which one actually describes it? And if we say that a universe was made for a purpose that involves beings who can investigate their environment, who have relationships with others, who can love and learn and all those sorts of things, we have an explanation which narrows the field dramatically. That is a property of good explanations, and that, I think, is one of the lessons of fine-tuning. Having reached there, let me quickly polish off with a few short comments on this whole science versus God thing. This is a very famous work of physics, in many opinions the first work of physics. This is called the Principia. It's by Isaac Newton. It was published in 1687. This is a first edition, a picture of a first edition, of which about 250 were made, so they're very rare. It's the most important, just about the most important thing ever published in physics. Okay? This one is actually even rarer, because if we turn to the next page, what you might be able to see there is Newton's own handwriting. This is a photograph of his copy, where he wrote some comments in the margins. But what you can't do with this piece of paper is say, there are two things here. There's what the printer did and what Newton did. There's no real difference between the stuff in the margins and the stuff that got sent to the printer. Where is Newton on that page? Newton is everywhere. It's all him. There is the stuff that, in order to make it neat and legible, was sent off to the printer and done in a very orderly way. And then there's the stuff that he sort of popped in the margins. When we look at the universe around us, if we look hard enough, we will see that there are patterns in the universe. If God exists, then there aren't two things. There are not the things that science can explain and the things that God does. Just as there aren't two things, the stuff that the printer did and the stuff that Newton wrote. There is one set of things, the stuff that God does. Some of that stuff is so rational and so precise and so orderly that we can describe it with some of the most elegant mathematics mankind has ever discovered. But it's all his. It's not the case that every time science has explained something, it sort of picked something out of the God did it pile. We've just described the pattern. Here's an example. Suppose you're watching an artist, Tyler, put together a mosaic. As you watch the pieces go up, you're not quite sure what the pattern is, but if you look hard enough, you should eventually work it out. As the bits start to come up, you might eventually work out what this pattern is. And at some point, someone might call out, it's a tortoise. At that point, the Tyler does not disappear into thin air. Hopefully everyone gets the point of this analogy, right? Saying it's a tortoise does not remove the need for a Tyler. Noting what the pattern is for the pieces does not remove the need for an explanation of how those pieces got there and why they are following that particular pattern. Right? There are no talks out there, Tylers versus tiling patterns. Right? There's no contradiction there. You don't get people saying, do you believe in Tylers? No, I just believe in patterns on walls. Doesn't make any sense. I think I'm getting through with this. Excellent. Good. Right? If someone works out the way electrons work, they've discovered the pattern that God imprinted into his creation. Right? There aren't two things. There is one thing. There is how God works in the universe, and so much of that is so precise that we can do science. There is a way that God's natural world works, and if we look at it hard enough and we're a bit clever, we'll work out some of those ways. I love this quote by physicist Poincaré. He said that we should be astonished by nature's regularity. Men demand of their gods to prove their existence by miracles. But the eternal marvel is that there is not miracles without cease. The world is divine because it is a harmony. Let me finish, if you've got another 2 minutes. I often get this question, so let me just sort of get ahead of it. Where does that leave talk of miracles? Something I get asked as a scientist. Can a scientist believe in miracles? So if you understand the sort of picture I've laid down so far, I think, let me just sort of flesh that out for you. Here's a reason why supposedly a scientist can't. This comes from a biologist from about 100 years ago, J.B.S. Haldane. He said, "My practice as a scientist is atheistic. That is to say, when I set up an experiment, I assume that no God, angel or devil is going to interfere with its course. And this assumption has been justified by such success as I have achieved in my professional career. It would therefore be intellectually dishonest if I were not also atheistic in the affairs of the world." Here's the idea, right? Scientists, according to Haldane, always assume that there are only natural things, and so it would be ridiculous for a scientist to assume that there was something supernatural. But I'm not entirely sure what Haldane has in mind here. He seems to think of a God who would just mess up our experiments. The poor lab technician is just trying to do her work, studying how bacteria grow or how chemicals react, and God steps in just to be annoying. Note the leap of logic there. Haldane doesn't have to assume that God does not exist. He merely has to assume that God is not a complete jerk. I think this is a very deep misunderstanding here, right? If we have that picture in mind of the one way of things, there is just the things that God does, and some of them are so precise most of them are so precise we can describe them mathematically, then there's no real contradiction here. Why would God run a universe in this way, where most of the things run via predictable scientific laws? I think we can get some part of an answer to that question. In our everyday life, we interact with each other, and we assume that the things we interact with, right, for each other, are going to be predictable. If you have to make a moral decision between, on the one hand, making a house, and on the other hand, making a bomb, you need to know what the stuff around you will do with some degree of predictability. You need to know that bricks make houses and that C4 makes bombs, right? If the universe around us were totally unpredictable, you might try and make a bomb and end up building a lovely house for someone. Okay? On that level, the laws of nature serve a greater purpose. They are the background in which all of the interesting moral stuff in our universe can work. We need that to interact with each other for moral actions to be meaningful at all. And I think this gives us an understanding of why we see a universe in which most of the things around us act via these natural laws. God has thought this thing out. There's no reason to keep stepping in and make it unpredictable. I think it also gives us a way to understand why God would do miracles in the first place. I think God would do a miracle if there was something about our universe which is temporary, something which is scaffolding, something whose time will be over, as a sign that its time will almost be over. So the way that I understand the miracle, the resurrection of Jesus of Nazareth, is that promise. There is something about the universe that will change. Okay? The pictures of this in Scripture are almost unbelievably optimistic. In Isaiah, he writes, "On this mountain the Lord of hosts will make for all peoples a feast of rich food, a feast of well-aged wine. He will swallow up on this mountain the covering that is cast over all peoples, the veil that is spread over all nations. He will swallow up death forever. The Lord God will wipe away tears from all faces." The meaning of that miracle is that it points to the thing about this world that will change: death, suffering. A God for whom death is no obstacle can put this world to right. So I don't believe in a God who plays pranks, annoying laboratory assistants, right? God really has dived down to the bottom of creation and has come up bringing the whole of redeemed nature with him. This is not one person's escape from the sufferings of our life, but God's stamp of his promise to make all things new. I believe in the resurrection as the exception that will become the rule. The power that made this world will remake it. That, I suggest, is a way of understanding how miracles can fit into a scientific worldview. So, if you want to read more about the things I've been discussing, the book is available at the back, and I look forward to your questions. Thank you.
Question number 1. How long have all the atoms in my body been around for in the universe? Have some been around longer than 39.5 years?
5 years. Answer to the second question is yes. The basic piece, it depends how much you break it down. The basic protons and neutrons, basically since the beginning. So in the very earliest stages of the universe, those are formed, and all they do after that is sort of combine in various ways to make nuclei. You need to generate the first after the Big Bang, all you have is hydrogen and helium. Basically, you can make stars out of that. They start to make the heavier things. So you need a second generation of stars to make all the other stuff in you that's not hydrogen and helium. Have all the been around? How long have they been? So second generation. Let me just try and work this out. Yeah. So probably a couple of billion years, maybe. I don't know. Depends on the person. I'd have to take a closer look. The typical lifetimes for the sort of star that blows up and sends its stuff out into the universe is in the tens to hundreds of millions of years. So you need that sort of time scale to produce them and then get them out. Good astronomy question.
Okay. Next question. Thoughts on evolution and the origin of life and how to reconcile it with the Bible?
Right, good. Let me sort this out once and for all. You start with the second one. I don't read Genesis. I read Genesis primarily as teaching us theology. I think I don't see it as giving any sort of scientific account of the origin of the universe. I think it's primarily there to teach us theology, especially in the face of the other, at the time, the other stories going around about how the world started. Those are great to go and read, by the way, the Enuma Elish, where you have chaos monsters fighting and ripping each other in half and forming the earth out of those bits, and then we're sick of this earth, someone else could look after it, so they make man, right? That's how we came about in that story. So to be then the pinnacle of creation, it's all good, there's order there from the beginning, is I think the theological point that's being made there. So I don't see any particular process or timeline from Genesis itself. That's obviously a huge issue that not everyone's going to agree with. That being the case, then if the pattern laid down is evolution, then that's the way God did it. If it's not, then it wasn't. But that's then purely a scientific question. That's you just look at the evidence and see what's going on, in particular the origin of life. It's a very hard problem, but maybe it was natural, maybe it wasn't. I think the thing we have to try and avoid is if I want God to explain it, I need to show how science doesn't explain it. Right? Okay. So if that's the same as saying if I want the tiler to explain it, I have to show there's something wrong with the pattern. That makes no sense. Right? This is God's creation. He does with it as he pleases. If he wants to make the order in the universe in one way rather than another, then he can and did. And there's no getting around that you have to put order and rationality and all of those things in at the beginning from the start in order to explain the universe we see. The picture of evolution as being totally random is wrong. It's a very orderly process. But beyond that, it's purely a scientific question. One of the problems is if you're an atheist, it's kind of the only game in town. So there's a bit too much at stake in scientific discussions of that, which makes it very difficult to be objective, no matter who you are. But you can always try. I'm not a biologist, so I don't know.
Okay, next question. What would you say to someone who objected to intelligent design if you had 2 minutes?
Say I'm talking again next week. So, just quickly, intelligent design, just as an idea, just that particular phrase, is obviously something that anyone who believes God created the universe believes in. The intelligent design movement, the movement in the US specifically, started by guys, William Dembski, Michael Behe, those guys, has been primarily aimed at showing that evolution is basically attacking evolution is the short story. The longest version of that is that when we look at the systems we see around us in the world, we don't see the output of any sort of mechanical process. We see the result of intelligent design. We can tell how intelligent agents work in the world, and when we sort of generalize that and then point that particular filter at biological things, they turn out to look like they've been designed. That then is just, if you're a Christian, like maybe that, or the way that God did it is very much an open question. So yeah, maybe support that or not. But what would you say someone who objected to intelligent design, if they're objecting to the movement itself? I don't feel any particular need to defend that movement. Maybe they're right, maybe they're not. But I think I'd want to keep coming back to the point I made earlier. You don't remove the need for a tiler by explaining the pattern, right? Even if the pattern there includes the pattern of the tree of life and of the evolution and common descent and all of that, it's still a pattern, it's still an orderly thing that needs an explanation.
Okay. If we assume, therefore, that God is our tiler, then why necessarily would he be the Christian God?
Worst case scenario, you say what God this is will have to be decided on other grounds, right? And if that's the worst case scenario, we say maybe it's the Christian God, let's go find out via some other method, okay? But I think, if one morning, an atheist, Richard Dawkins walks out of his front door and looks up at the clouds and they spontaneously arrange themselves into the sentence, "That's enough, Richard." He'd still have the question, is that the Christian God? Who's sending me a message? The thing he should do with that question is try to answer it, because someone is sending a message, right? So I think worst case scenario, we just say this God idea is worth taking seriously. I should look into it further. I think there is possibly a deeper method there. I'm quite impressed with, particularly in Christianity, the idea of the Trinity, the idea that loving relationship is part of what God is, not just something that God does. So if you think that the thing that explains why there are intelligent agents in our universe, why there are beings like us, is that they serve some sort of purpose, that love is good, and so things that can love is a good thing that a good God might want to do. If that's part of the explanation, as I think it needs to be, like it can't just be some random God who enjoys just making things at random, right? That won't explain things. A God where that sort of concern for loving relationships is central to the idea of God, I think is ahead of perhaps other ideas of God which don't have that. But that's a very tentative step towards Christianity. If we've gotten this far, you should keep pushing on to find out who this God is.
What if we encounter extraterrestrial life?
Depends if they're friendly or not, I guess. Watch too many movies. What if there's extraterrestrial life? I don't think there's... This is supposedly a problem for Christianity. Like, what does it mean for us if there's other forms of life out there? I don't see any problem. I mean, even if you're a young Earth creationist. I mean, I've never met anyone who thinks that Genesis is sort of a limit of what God has done in the universe, right? I mean, literally the creation of the rest of the universe goes like this. He made the stars also. It's 5 words in Genesis 1, right? If God wants to do other things out there, it's his business. So if there's other life out there, then fine. Everything else is speculation, and if you want to speculate on that, then you should go and read the Space Trilogy by C.S. Lewis, where he speculates about what if there was life on Venus and what if there was life on Mars and those sorts of things. But I think there's no... If we encounter extraterrestrial life, it might suggest that either God, if life needs to be specially created, then God had other purposes for other people out there, or if life is something that can happen naturally, then God created in his providence the place in the universe where that would happen. It's entirely up to him.
Is the faith required to believe in the multiverse any more substantial than the faith it takes to believe in a creator?
It looks like this question is assuming that faith means belief beyond evidence, and that I object to. All right? That is not the New Testament's definition of faith. Okay? Faith is trust. So you don't put your faith in the multiverse because you don't trust it. It literally has no effect. If there is one out there, it literally has no effect on your life whatsoever. Right? It could all totally disappear tomorrow and make no difference to any of us because it's beyond what we could even possibly see. There's a terrible old joke, which you've probably all heard because it's one of the 5 jokes you hear in church. But if you've heard it, tune out for the next 30 seconds or so. There's a tightrope walker who's put the tightrope across Niagara Falls. Some of you have got this already. Okay, he goes across and back, and the crowd cheers, and they want him to do something else, something more. So he throws away the pole across and back. Bigger crowd, they're loving it. He gets a wheelbarrow across and back, puts a sack of potatoes in the wheelbarrow across and back, and the crowd is going ballistic. He's giving it up to the crowd, and he goes, "All right. Do you think I could do it with a person in the wheelbarrow?" They go, "Yeah." "Do you think I could do it with a person in the wheelbarrow?" "Yeah." "Do you think I could do it with a person in the wheelbarrow?" "Yeah." "Can I get a volunteer?" All right. Belief is, yes, you could do that with a person in the wheelbarrow. And faith is getting in the wheelbarrow. Okay? That is the Sunday school definition of faith. So, is it more likely that there is a creator than that there is a multiverse is the question. Which way does the evidence point? Okay, is an open question. So for Geraint, my co-author, the problem for him is that he thinks God is a bit of a non-explanation. You're trying to explain natural things which we're all familiar with, and to explain that we've invoked something totally beyond what anyone has ever experienced, a totally unnatural, if you like, or supernatural kind of thing, and that's what makes it a bad explanation. It is certainly true that there is a level in which we're never going to know whether the multiverse is true, so whether it's a scientific theory at all is a bit of an open and hotly debated question, even amongst cosmologists. So what I'd want to say is, even if there is a multiverse, that might have been the way that God has chosen to make a life-permitting universe. That might be a particularly simple way of doing it. It's not like he has to put in any extra effort to do it, right? I mean, there's life on this planet, but God has made other planets and other stars, right? So if that's the way God wants to bring about that the state of affairs he wants happens, then so be it. So there's not necessarily a competition there. I think even if Alberta's blackboard has the equations for a multiverse, you still have all the same sorts of questions. What we would like to do is change the parameters of the multiverse to see whether they make life-permitting universes. We can't really do that. But all the same questions would come up about why that particular set of laws, and I think in that case a creator would still be needed to explain.
Okay. Is it true that the sun is going to explode? If so, is this not a way to measure when it will be the end of the world?
The sun is going to expand before... No, it's not going to explode is actually the short story, but it is going to expand until it gets bigger than the orbit of Earth, which is bad news. When it runs out of hydrogen... So the same scientific models we use to explain the current properties of the sun, we run those forward in time and see what happens. So this is how we think we know what will happen. When the sun runs out of hydrogen, it has to sort of adjust to start burning something else. It starts burning helium. In that process, it will expand. The good news is that, what's today? Thursday, the 7th?
11th?
Yeah, so it's 5 billion years from next Tuesday. So we're going to be all right. But, I mean, by then, if we haven't worked out how to either just, like, slowly over 1 billion years just move the Earth out a little bit or just get off and go somewhere else, then, I mean, what were we doing for the last 5 billion years? Is this a way to measure when it will be the end of the world? I I take the picture of the end of the world to be supernatural. It's wiping the chess pieces off the board, right? It's not following the rules to make sure everything gets off, right? So you can then play checkers or something, right? I made this for a purpose. That purpose is now over. I'm going to remake it, right? I'm not going to follow the rules I put down, right? Real bishops don't move diagonally, right? You don't have to obey the laws of the game that you invented. So how the end of the world happens is entirely in God's hand. He could do it via completely natural means, but who knows?
Okay. Is the universe homogeneous?
Homogeneous, meaning it has the same properties everywhere. So, this is a good cosmology question. Excellent. The answer is, in short, obviously not. There's more matter here than there is here, for example. What we've noticed about the universe is when you map out galaxies on a very large scale and then sort of zoom out a bit, it's almost totally uniform. And the more you zoom out, the smoother it looks. So on large enough scales, the universe looks homogeneous. So just like the air in this room is homogeneous, there's roughly the same amount of air over there as there is over there in any sort of small volume. But if you zoomed in enough, you would see individual atoms. That's the assumption that started off cosmology as we know it. It started off as just what's the easiest thing we could look at in theory, because Einstein's theories are hard. And then we found out actually the universe is like that. It was almost a toy model, a practice problem, and then we turned out not to need anything else. That's the universe as far as we can see. Light only moves at a certain speed, so you can only see so far into the universe. What happens beyond that is unknown, obviously, because we don't have any information. So the observable universe is homogeneous, or homogeneous, however you say that. We've measured that. The universe as a whole, including beyond where we can't see, is an open question. And it depends what sort of assumptions you want to make. It would be odd if we were in the one bit of the universe that was perfectly homogeneous, is all you can say.
Okay. Was there a Big Bang?
Ooh, good question. So there's two things here. When scientists talk about the Big Bang, there's kind of two things. One of them is what you might call the Big Bang theory, which is basically a theory about how the universe changed over its life. Basically, all it says is in the past, the universe was denser and hotter. And that's basically it, okay? So you run the clock backwards, that simulation I showed, just run it backwards. You get a universe which is denser and hotter. And it turns out that idea about the universe predicts a whole heap of stuff which is actually true. You go back in the earlier stages, it's hot enough to light up nuclear reactions. You can ask how much of the protons we started off with would be burned into helium, and then we go and check that answer in the universe, and it turns out we got it right, which is interesting. So there's that theory, but you're sort of starting today and trying to work back in time, and you can only do that as far as you trust the equations that you have to describe the universe. As long as you can sort of predict what stuff will do, you can push things back to say what would have happened here, what would have happened earlier on. There's a limit to that in the early universe. It's very short, shortly after the beginning, tiny fraction of a second, but beyond that we don't know. So within the sort of standard picture of cosmology, the Big Bang is the initial starting point in time, before which there wasn't time at all. That sense of the Big Bang, it's there in some of our models, but we suspect that our models are incomplete before we get to that point. So was the universe in its earliest stages dense and hot? There is very good evidence for that. Was there a beginning of time where everything was compressed into a point and it was infinitely dense? We don't know. There's an awful lot of we don't know in this talk, sorry. We're working on it.
Okay. How would you explain the elements created by the Big Bang Theory in relation to God's creation of the universe?
So one of them is what does natural things do, and the other one is what is God doing, right? They're not two things, one thing. The elements created in the Big Bang Theory, as I said a minute ago, in the earliest stages, things were hot enough for nuclear reactions to turn some hydrogen into some helium. That's pretty much all you get from the earliest stages. We can sort of run the clock backwards and predict things about our universe using that, which is why we think that that idea is correct, and there's other sort of evidence. It's then a different question entirely of how does this relate to, if God is the creator and sustainer of the universe, then that is the pattern that he chose to run his universe by. It's a bit like asking, how would you explain the relationship between Harry Potter and Hermione in relation to J.K. Rowling's authorship of Harry Potter, right? They're just two different levels of explanation. One is, what's the story, the internal story of the characters of our universe, how they've interacted with each other. Over above all of that is the author.
Okay.
Why is the universe composed of just 4% regular matter if the universe is fine-tuned for humans? And why humans compose just, that is maybe 10 to the power of minus 52, or I'm not sure exactly what the number is, but obviously either a very different ratio. So I'll start again. So why is the universe composed of just 4% regular matter if the universe is fine-tuned for humans? And why do humans compose just 10 to the power of 52 of this universe? It seems like Occam's razor would point towards naturalism due to the extremely non-human-centric ratio.
Right. So the question is, why do you think the universe is fine-tuned when so much of it is inhospitable to life, is the short version of that question. So the first part of that is, when we do the accounting on the universe as a whole, the stuff that we're made of, that type of matter only makes up about 4% of the whole. There's something called dark matter, which behaves gravitationally like matter. It's attractive, but it doesn't do the sorts of things that matter, as we know, does. And then there's something called dark energy, which is even weirder. We can talk about that later if we want. Why would that be the case? I think we can get a bit of an answer for that, to be honest. The dark matter is useful because it doesn't feel the pressure of ordinary matter, which actually holds back the collapse. So dark matter collapses earlier in the universe, forms a sort of the backbone of that structure, the cosmic web, in which then galaxies form. So actually galaxies form more efficiently if you have dark matter. Dark energy, I think we're actually literally running simulations at the moment, changing the amount of dark energy to see what happens. There are various reasons why it could serve a point in this universe. There was a scientific paper, I think last year, which said it's actually quite useful because it means galaxies aren't so dense, so you don't end up with all of your planets in regions where there are also supernovae, which is a bad idea, or gamma ray bursts, never mind. So it's actually useful to have something which sort of spreads the universe out a bit. But, I mean, more generally, you've got to weigh up the different explanations here. So if you have all the possible values of how much dark energy could you put in the universe, if you say, well, we want our universe to do something interesting like make structure at all, and because the interesting things will be sort of morally valuable things, over that huge range, you now need to be there to be a very small range which will actually allow structure, and all of these universes are ruined in the way that I showed. So that's the advantage of that explanation. If you're a naturalist, there's no a priori reason to think that the universe would contain structure at all, and so you still have that huge set of possibilities. You're looking at the whole Guess Who board without the slightest clue as to which one of those is going to be the actual universe, and that's not a good situation to be in. Right? In probability theory, we call those non-informative theories. You have a huge set of possibilities and nothing more to say about which one of those possibilities is the actual world. That, I think, is the shortcoming in naturalism, which is exposed by fine-tuning. So, in particular, why are human beings so small with respect to the rest of the universe is an interesting one, but it's kind of an old one. You often see this presented as science discovered that we're really small in the universe. That's a sort of discovery of modern science. It's not. The Earth should be treated as a speck with respect to the rest of the universe. It's something that was said by Ptolemy in 2,000 years ago. He was an early astronomer. And Psalm 8, what is man that you are mindful of him when I consider the heavens? So that's not a recent discovery. Why would we be small? Well, there's a couple of reasons there. You can be small and morally valuable, right? You don't measure significance with size, okay? There's a very esteemed cosmologist in Cambridge when I was there, the sort of local legend of the department called Martin Rees, who I really wanted to meet. And he walked into the room and he's really short, right? We don't measure importance by size, okay? My kids contribute nothing to the structural integrity of my house, nothing, right? If there's a fire, I'm not going back for the load-bearing beams, right? I'm going back for my kids because they're the important thing, right? You don't measure importance with size. There's the alternative to this question would be, what would you like a larger fraction? Would you like to be in a universe where the complete sum of all the stuff in us made up half the universe? It was just us crammed cheek by jowl into the universe with nothing else to look at. What sort of universe do you want, right? Do you want one that is awe-inspiring and perhaps points towards an awe-inspiring God, or a nice little cosy one, right? There are reasons why God would make us small relative to an infinitely large universe, potentially infinitely large, at least huge universe. It's kind of sending you a message about how important we are in the cosmic scheme of things. So, the point of this question is if you put it as a statement, it would be, if God exists, he would make a universe in which humankind was more bigger in the universe. Would you make a universe smaller? I don't see any reason why that would be true. And in particular, the fact that so much of the universe is empty also plays a part in making it habitable, right? If you fill the solar system with air, it'll be great. You could go breathe on your way out to Mars. The orbit of the Earth will last a couple of months before, due to air drag, it'll get sucked into the sun. So that's a bad idea, okay? The emptiness of space plays a role. We can see the stuff that's out there, but it doesn't affect us. We're stuck down here with all this oxygen, right? You have to go an awfully long way and work very hard to fill the vacuum of space. It's not coming to get you. You often hear popular science saying the universe is out to get us. It is the least effective assassin in the history of the world. If it's trying to do that, it literally, a meteorite kills one unfortunate bloke in Asia somewhere, and there were 3 Russian cosmonauts who died in the vacuum of space because their spacecraft malfunctioned, and that's basically all the people the universe has killed. Right? We're doing fine down here. This part of the universe is serving its purpose as being somewhere where moral actions are meaningful, but where we can see something bigger and more grandiose and more in equal parts beautiful and terrifying, the universe as a whole.
Dr. Barnes, I'm aware our time's come to an end. Just as a final question, for anyone in the room that science is that big intellectual hurdle that they can't jump over to even begin a journey or an investigation into a God, what would you say would be a helpful next step?
I've got a book you can read.
Set you up there.
Yeah, cheers. Look, the book was co-written with an atheist, so it's not just, a one-sided, one-eyed view of the whole thing. So it's not a bad place to start. There are, people who started life, where science has led them to God. That deeper understanding of I see order and structure here, and if I do all the science that I can do, if I discover everything there is to know about the universe, if I write it all up on a blackboard, I'll be staring at order and beauty and structure there as well. And I need a picture which is big enough to explain that as well. And science itself, if you assume that it's it, or naturalism, where you assume that natural stuff is the only stuff, is not enough. You're still going to be left with questions about the universe. So guys like Alan Sandage and Francis Collins, who's the head of the Human Genome Project, and Alistair McGrath, these are start digging into books and start reading about what these guys think.
You thank Dr. Barnes for me.